All right, welcome to this explainer. Today, we are digging into what I can only describe as an absolute engineering heist. We're going to look at how some seriously brilliant developers used ancient number theory to literally tunnel straight under the rigid constraints of blockchain math. If you've ever found yourself wondering how the true next generation of decentralized finance actually works under the hood, how it translates these crazy abstract mathematical concepts into physical on-chain execution, well, buckle up because you're in for a really fascinating ride.
Okay, let's dive into this counterintuitive, kind of mind-bending problem. How exactly do you do trigonometry on a computer that literally cannot understand decimals? I mean, it sounds impossible, right? But as you'll see, the relentless push to build the cutting-edge future of DeFi basically forced developers to resurrect this concept of division-free integer geometry. And the solution they came up with? It completely reimagines how we process math on a blockchain.
So, here's our roadmap for the explainer today. First, the blockchain decimal problem. Second, Orbs swaps polar compromise. Third, the FPU gambler's toll. Fourth, enter the ALU surveyor. Fifth, base scale calculus AMMs. And finally, number 6, the era of exact truth.
Let's kick things off with Section 1, the blockchain decimal problem.
So it all boils down to this foundational concept called EVM determinism. This is the absolute strict requirement that thousands of globally distributed nodes in a decentralized network have to reach the exact same mathematical state. No exceptions. Because of this, native floating point math, which is just a fancy way of saying decimals, is structurally forbidden. Think about it. If the blockchain tries to use decimals to calculate a curve, different computers might round off those tiny fractions just slightly differently. And if they disagree by even a hair, consensus instantly breaks, and billions of dollars could literally just vanish into thin air. So developers are backed into a corner. They have to do complex math using only whole, exact numbers. And this brilliantly illustrates the core divide in how hardware processes math. On one side, we have the floating point unit. I like to call this the FPU gambler. It's blazing fast, sure, but it's lossy and probabilistic. It essentially approximates complex math by frantically throwing darts at a board to guess the closest answer. On the exact opposite side, we have the arithmetic logic unit, the ALU surveyor. The surveyor is incredibly strict, totally discrete, and deals strictly in 100% exact, deterministic hardware truths. 1 plus 1 is exactly 2, every single time, on every single machine on Earth. It gives us universally verified truth, without any rounding or guessing.
Moving on to Section 2, Orb swaps polar compromise.
Now, OrbSwap had this incredibly ambitious vision, right? They wanted to build an n-dimensional automated market maker specifically for stablecoins. Instead of using traditional Cartesian math, sliding along your standard x and y axis, they utilized a super ellipse invariant. They basically treated the liquidity pool like a circle, calculating trades by rotating around a focal point using polar coordinates and trigonometric angles. On paper, this is incredibly elegant. It allows for highly granular multi-token liquidity. But, and this is a massive but, navigating this exact grid requires calculating really complex angles using heavy trigonometry, like sines and cosines. And as we just established, the blockchain absolutely does not speak trig natively.
Let's move to and see how this builds out into an actual solution, or, well, a workaround. To make this work, OrbSwap had to construct a massive illusion. They started out with beautiful theoretical continuous math in their research. Then, they deployed WebAssembly smart contracts via Arbitrum Stylus, writing their code in Rust using 64-bit floating point, or F64 variables. But because the EVM can't actually handle those floats in production, they had to forcefully translate them into EVM integers. How did they pull that off? By relying on gas-heavy EVM integer scaling libraries like PRB math. They're basically multiplying values by massive 10 to the 18 scaling factors, known as WAD scaling, just to mimic decimals. It's a complete emulation trick.
That brings us to Section 3, the FPU gambler's toll.
This scaling workaround reveals a pretty stark reality when we look at the actual costs. Relying on emulated FPU math to process those polar coordinates, it completely erases the execution efficiency of WebAssembly. I mean, just look at the numbers on this table. Basic native integer math on Stylus costs around 1 to 2 gas, super cheap. But an emulated soft float edition, that jumps to 12 to 25 gas. Multiplication spikes up to 30 to 60 gas. And division and precision scaling, they rocket up to a massive 80 to 150 gas. So that mathematical elegance of polar coordinates introduces a totally crushing execution penalty on chain.
And the cost isn't just financial, right? It's structural. We call this the wood chipper effect. When you take a bad guessed decimal from the FPU gambler and multiply it by a gigantic number to force it into an integer, you compound the error. Emulated rounding permanently destroys exact mathematical provenance. As our sources point out, it's literally like a giant blender. You can't reverse engineer a smoothie back into the original fruit. During periods of high market volatility, this severe, non-deterministic numerical drift leaves the liquidity pool incredibly fragile and totally vulnerable to rounding exploits.
This perfectly sets up Section 4, enter the ALU surveyor. To build automated market makers that are truly secure, developers realized they had to deliberately ditch this floating point trigonometry completely and resurrect ancient division-free math. I love this quote from the architecture documentation. By using the Pell-Smith stride, we move from approximating a curve to mathematically possessing the exact, indisputable state of the manifold. This is a monumental leap. We are totally moving away from those sloppy spatial approximations that invite the gambler, and we are stepping entirely into absolute, undeniable, bit-perfect truth. Let's look at how this works in Section 5, Base Scale Calculus AMMs.
Here is the absolute crucial difference. While orb swap relies on those gas-heavy EVM integer scaling libraries like PRB math to just emulate decimals, the best-ape AMM test repository uses a totally different methodology. It's called base scale calculus. Instead of using Taylor series to blindly guess decimals, this framework relies solely on exact integer sequences, specifically Pell-Lucas recurrence relations. It totally replaces trigonometry with discrete rational lattices, eliminating the need for decimal points entirely. It calculates perfect ratios of exact integers to efficiently approximate irrational numbers directly on-chain. It's just a remarkably elegant way to build AMMs using only pure, whole numbers.
And the way they maintain structural stability without ever relying on those heavy scaling hacks is just pure genius. First, they anchor the entire coordinate system to a = 1, which is known as the transverse constant. Then they completely throw out that messy trigonometry and replace it with discrete reciprocal shifts across a rational lattice. Finally, they utilize global remainder tracking natively. Because absolutely everything is handled via discrete shifts rather than spatial approximations, the system achieves strictly unbiased similarity estimation. You get perfect mathematical fidelity without ever asking a computer chip to throw a dart at a board.
Which brings us to our final part, Section 6, the era of exact truth.
Now, what's really interesting about this slide is the sheer scale of the efficiency gained here. It's incredible. When you replace floating point math with pure integer geometric rigor, you aren't just gaining accuracy. The metabolic energy required to run these operations drops to an astonishing 0.05 picojoules. That is a staggering 74 times reduction compared to standard floating point methods. It completely obliterates the gas cost and energy required to perform exact coordinate rotations.
This brings us to the underlying philosophy of all this, a concept called quantiscale. Quantiscale treats market increments not as arbitrary ladders or continuous spaces, but as emergent recurrence grains. It recognizes that by using exact integer sequences, we can finally map the messy, volatile reality of actual financial markets directly onto the uncompromising deterministic grid of the ALU surveyor. We are no longer approximating reality, folks. We are mathematically possessing it. So, we've tracked this incredible journey, right? From the strict limits of blockchain decimals, through the perilous approximations of the FPU gambler, all the way to the absolute precision of integer geometry. By marrying structural mathematical order directly to the execution layer, the bridge from digital truth to physical reality is officially wide open. So I want to leave you with one final provocative question to chew on today. Now that we finally possess absolute mathematical truth, what will you program it to do?